Hi, Amy Sterling here with FlyWire. Welcome everyone to the FlyWire Data Challenge Award Lecture. We've got David Garcia-Soriano visiting live in Princeton, and this is live streamed. So thank you all for joining. And before I pass it over to Ari and David for the lecture, I just wanted to give a quick little update on some things with FlyWire. So as you know, the Data Challenge is pertaining to the FlyWire brain here, which is, the whole fly brain. But you're probably aware that we have recently started proofreading and annotations in the bank. So I just wanted to give a really quick update on that front. The bank is approaching 1 million edits. We have 36,000 proofread backbones in the bank. And over 13,000 cell info annotations. So thank you so much to everyone in the community who's been adding to this data set and helping make this resource, because these edits and annotations are available in real time to the community. So I will stop sharing with that. Just wanted to say a few quick words. There we go. My video's on. And Ari, I will pass it over to you guys for the actual lecture part.
Thank you, Amy. We're excited to have David. It's an honor to have you here in person. This was a very tight competition. I would also like to thank everyone else who participated in the data challenge, especially Xin Zheng and Tatsuo Kuko, who teamed up and came third place. And Ben Tedigo from Allen Institute, who came to second place within very tight margin, and the competition was going all the way to the last hours of the deadline. There is a new challenge up, so feel free to go check it out in Codex. It is also about using connectivity and connectome-based methods to analyze the fly brain. I guess David, take it away.
You might need to admit some more people, right?
Yeah. Amy, can you admit?
Yeah, I can handle the admissions from here.
Thank you. I guess so. Just make sure. Do you see our screen, Amy?
No, I do not. There we go. There you go.
Okay, thank you for having me here. I'm going to say a few words about myself. I studied math and computer science in Madrid, and then I moved to CWI Amsterdam, where I did my PhD in theoretical computer science. And that's where I met Ari, and we did a lot of a series of very nice papers on property testing, which are super simple, efficient algorithms that they don't have time to process all the data, but they still to give an answer as to whether an object satisfies a property or not. And you need to do it in a provable manner, like you need to prove mathematically that with high probability the answer is correct. After that, I started applying these techniques to data science. So these days I'm working on data mining, scalable machine learning, algorithmic fairness, and clustering, of which we'll see some great examples there. I've been doing my career in industry and academia, but in the end I decided to focus fully on academia. So I became a tenure track assistant professor at the Technical University of Catalonia in Spain. Okay, so that said, let's go right down to business. How can I? Okay. So what was the challenge about? Well, so the problem was to analyze the visual columns, the connectome of the Drosophila. Basically, we have a certain number of neurons of 31 distinct types that have already been obtained. And now the task is to challenge, the task is to partition the neurons into columns, okay? These columns, each of them will be responsible for processing the visual information for a specific region of the visual field. And we assume that each column usually contains one neuron of each type. So basically the columns will be clustered of size 31, one per type. Now, currently this is being done manually. So this is a laborious task. So the challenge was to automate this process if it is possible. So what data do we have available? Basically, we have the type of each neuron, and the synapse counts between neurons. And the task is whether we can find the columns efficiently. Okay. If I translate this problem into a more abstract graph problem, which I'm more familiar with, what we have is a weighted graph with 20,000 vertices and 200K edges. I will consider this graph to be undirected because it doesn't really change much. And the vertices are colored. So basically each color corresponds to one of the cell types. Now our task is to partition the vertices into 796 clusters. So basically what I call cluster was what you guys call columns. Plus we have a special throwaway cluster, I call it the garbage cluster, in which we can put whatever doesn't belong, basically. But the constraints that we need to satisfy is basically that we cannot have two nodes of the same color in the same cluster. Okay, basically we have it. This will force the cluster to be of size of at most 31. Most of them will be complete in the optimal solution, but some of them will not be complete. Okay, and what is the objective? Our objective is to maximize the weight of the internal edges. Like I look inside its cluster and see how many synaptic connections there are. Or equivalently, it is to minimize the weight of external edges between clusters. These two things are the same because the total number of edges is fixed. So if you maximize one, you're minimizing the other. At least for exact algorithms. So when you talk about approximations, then the meaning changes slightly. It's not the same to have a two-factor approximation for one. It's not the same as having a two-factor approximation for the other. But let us focus for the moment on the minimization version. Okay. So the first thing I did is to phrase this problem as a correlation clustering problem.
But is this called, what would you call this, multi-class assignment? Kind of, it's like an assignment.
Multidimensional assignment.
Multi-dimensional assignment?
True. That yeah, you can also cast a multidimensional matching problem.
Right.
I took a slightly different route. I phrased it as a correlation clustering problem. Basically, correlation clustering is the most natural formulation of clustering. Let's start with the simplest case, which basically, okay, what is clustering? In clustering, you need to group together objects that are similar, and objects that are dissimilar to each other have to be in separate clusters. So let us assume that you have some graph with information of whether two objects are similar and should be grouped together, and what objects are dissimilar, in which case I don't put an X. What is an optimal clustering? It's a collection of cliques, like everything inside the cluster is connected, and there are no edges between clusters. Of course, this will be possible in practice unless your data is perfect, or I mean, this is an unreachable goal for most simple distances. But correlation clustering attempts to find the clustering that most closely resembles a collection of cliques. So basically, we're going to penalize edges between clusters, and we're also going to penalize missing edges inside a cluster. This has lots of applications in documented duplication, clustering gene expression patterns, span detection, image segmentation.
Sorry, click means connected.
Come again?
Click means.
Yeah, a click is a complete graph. Like all pair of nodes are connected.
Maximal.
Yes.
So by click here, you mean maximal click? I don't understand.
No, what I mean is that if you have a click on K vertices, then you have K choose two connections between them. That's a click.
Right.
Now, that would be the perfect cluster. In general, given the instant, you won't be able to partition into a collection of clicks so nicely.
Okay.
But you can consider the errors, like you consider errors with respect to a clicks, basically.
Okay.
This I consider an error because there's a missing edge, and I also consider it's an error because there was an edge between these two, but they belong to different clusters. Okay,
The number on your previous slide, 796, you were given that.
this is the
from
number of
start.
clusters.
Okay. You don't have to find it, you.
No, it was part of the
Okay.
challenge, yeah. Okay, I described the basic setting in which the edges are not weighted. You can consider a similar setting in which you put weights on the edges. So in a weighted correlation clustering, you need to find a cluster function. Basically, you assign a number to each vertex in such a way that you minimize I mean, you assign negative and positive weights to the edges, let's say, and then you penalize whenever there's a edge of positive weights. But you cluster these two vertices in different clusters, you penalize it. And you also penalize whenever there's an edge, a negative edge, but you're putting them together. Okay, how does this relate to the original problem? Well, in the original problem, I can do the following. I put an edge of positive weight with the number of synapses between two vertices. And also I put an edge of negative weight between two vertices if they have the same color. And this, this negative edge has actually weight infinity. What does that mean? It will force the optimal solution to never put together two vertices of the same color. So basically, this part will ensure the constraint that we cannot put together two vertices of the same color, and this part takes the task of minimizing the number of edges across clusters. Now, what happens with this problem? This is NP hard, there's no exact solution, but there are approximation algorithms. In fact, there's also an approximation scheme for when you fix the number of clusters, but let us ignore just for the moment. The thing is that this is a very well-studied problem. There are lots of algorithms for this. Actually, this year I published a book on this topic with Francesco Bonchi and Francesco Gullo. So far, so good. We have phrased our problem into something that has been extensively studied. I also have a book about it, so let's call it up and run away with the first prize, right? Unfortunately.
Signing copies after the.
I should have brought copies. Well, it doesn't look very well.
Special price for you.
My point is that in the end, it wasn't so simple, but okay, that was the hope. And the reason is the following: when the existing algorithms to solve this problem basically start by solving a linear program. A linear program is just a mathematical optimization program where the constraints are linear, and then you apply some kind of rounded algorithm to get the actual clusters. Okay, so you can see the program here. Basically, you're going to have a variable that tells me if U and V are in separate clusters. So it's like a measure of distance within clusters. And then I'm going to say that if you have two vertices of the same color, they need to be in different clusters. Now we have this triangle inequality constraint that enforce transitivity. Basically, it means that if I put U and V in the same cluster, and I put V and W in the same cluster, then I also need to put U and W in the same cluster. Right? It's like a transitivity. Okay. Now, when you solve this problem, you will get some solution with fractional values, while in the end you want integer values 0 or 1, whether they're together or not. But there are some rounding schemes that allow to obtain an integer solution from this based on region drawing. Now, what is the problem with this approach? It has too many constraints, like n-cube constraints, like if n is the number of vertices. They also have too many variables. So, while this is the best approximation algorithm for this problem, it's not even, it's a non-starter for the challenge. We cannot really apply this. So that's the right loss. Okay, so what did I do? First, I took inspiration from this. Okay, I say, I'm gonna write another program that first of all is gonna allow me to prove a lower bound on the optimal solution. Even if I don't know what the optimal solution is, I'm gonna find how close to the solution is the starting solution that I provided. I'm gonna see if it is far or close to optimal. And for that, I look at the problem differently. I say, okay, suppose that I take my graph and I put a variable. If I cut an edge, I'm gonna start removing edges from the graph. Okay. After I remove a certain number of edges, I can look at the connected components that remain in the graph, and this will be my clusters. So basically, my objective function is going to be minimize the number of edges that I cut, subject to the condition that I cut all paths between vertices of the same color. Okay. This is what this program writes. It has an advantage. It has very few variables. Only the number of variables is equal to the number of edges, but it has an exponential number of constraints, basically one for each possible path. So what did I gain by this? It seems I didn't gain anything, but I did. First of all, this program is efficiently solvable, even though the number of constraints are exponential, because it has what's called a separation arc. But second, the number of variables is, it's very small. What I can do with this is I'll take another route and write a subprogram of this with
Sorry, I
a,
missed why it's exponential.
well, because the number of paths can be exponential, right? I mean, I
So
write the
U
constraint.
and V could be any, U and V are just two vertices in any path.
Yeah, no, but basically for every path, the sum of all the edges inside the path.
I see.
So I'm gonna say the edge from the first to the second plus second to the third, plus
Okay.
the third to the fourth. So there's a path of length 4.
Mhm.
I mean, you might have to write like n to the 4 constraint there, you know?
Okay,
But it's an exponential number of constraints. What we can do is to reduce it. Okay, let's just consider all paths of length 3 and 4. Okay, so instead of trying to separate all these vertices completely, I'm gonna ensure that there are no short paths between them. And in this case, I can solve it exactly with an integer programming solver, with a commercial solver called Groovy. Basically, if I can cut all paths of length 3 by removing 700k edges. And the solver also told me that to remove all paths of length 4, I need to remove at least these many edges, like 75k edges. Okay. So this is already quite close to the starting solution of the challenge. It's within 5% of it. So we have a solution which costs 811k, and I can show that any solution, the optimal solution, needs to cut at least 775k. So
Would you run for 5 as well and continue, or was it too big for the?
it was too big. Yeah.
what's the algorithm used by the solver?
Well, it's
Is it
commercial,
also-
but it's I mean, basically it solves the linear program, and then if it finds a solution with all integer variables and it's done, otherwise it finds Gomori cuts. I don't know. Basically, there are constraints that need to be satisfied by any integer solution, even if they're not constrained in the original program. And that's adding that in a smart way, and they're doing this.
Okay.
Okay, so I mean, I got a lower one, and what that told me is, okay, we're already pretty close to the optimal solution. So let's start, instead of trying to find a new solution from scratch, let's start to modify what we have.
Well, you only know in retrospect.
No. At this point, I haven't even improved the original
But how do you
solution.
know? Oh, you say that, I see.
Because
So there's
it's,
a lower bound too.
yeah, I mean, I know that to remove all paths, in particular, I need to remove all paths of length 4, right?
Mm,
And I know that to remove all of length 4, I need at least as many.
okay,
So the true lower bound would be actually higher. This is the one I.
okay.
Okay, so I need to start doing local improvements to improve the solution. One naive idea would be, okay, I look at every pair of vertices and try to swap their clusters and see if it improves the solution. But this is too slow. We need a way to do this kind of swaps in parallel. My idea here was to consider all vertices of a single color. Now, the nice thing about the vertices of a single color is that they form an independent set, like there are no edges between them. Because if there were, we would have removed them from the spread. And it turns out that in this case, if you take a solution, then remove all the vertices of a color 1, let's say, and then you're trying to find the optimal assignment of all these vertices to the cluster, the existing clusters, you can solve this efficiently via weighted matching problem that can be solved via the Hungarian algorithm. Basically, you build a bipartite graph. On one side, you have the vertices that the user removed. On the other side, you have the clusters. And then you put an edge of a certain way with the number of connections that this vertex has to that cluster. And this works because of the constraint that you cannot put two things of the same color in the same cluster. So you don't need to worry about if I put 2 of these vertices that I removed in the same cluster, I don't need to account for the edge between them. Okay. In general, this works actually with, if you remove any independent set, it doesn't have to be the vertices of the same color, but in practice, I didn't find any improvement by considering more general independent set. Anyway, if you do it the right way, then after 1 minute, you will improve the solution by 200k edges. But I wanted to win the challenge, and this was not enough. So back to the drawing board, okay? But
But if you started with that, without the integer programming solver, would this?
no, yeah.
Would this be enough?
Yes, this you can do without the integer programming. The integer programming was a first step for me, was
Okay.
not necessary
Okay.
for this.
Okay.
But I think it's quite interesting to have a lower bound. Okay. For the second, I mean, the third step, I took inspiration from a very recent preprint by Cohen and et al. About correlation clustering. Basically, they consider this operation in which given current solution and an arbitrary subset of vertices of distinct color. They consider the solution that you take if you recluster all these vertices into a new cluster. So you remove them from the current clusters and make a new cluster with all these vertices. Now, suppose that you could find this solution efficiently, which you cannot, but let's suppose that you could. And suppose you could do this iteratively until no longer improvement is possible. Then they show that this solution that is robust against local swaps is also close to optimal. Okay, they show that it would be a two-factor approximation. Now you might say that you don't care about two-factor approximation because I already have a solution that is within 5%, right? But for me, this was pretty interesting because it shows that there is a link between local optimality with respect to a certain swapping property and global optimality. So I decided to try this. And I wrote another integer program.
So what is the swap again?
The swap is find a cluster, find a set of vertices so that when you perform this operation, the value of your solution is maximized. And this operation is you reassign all the vertices to a new cluster.
This is adding a cluster. This is adding a cluster.
So basically, this subset of vertices, C.
Yeah.
They may be assigned to some cluster currently. Remove them from the current assignment and put them together in a new cluster C.
Right, so it's a move that
It's a move.
increases the number of clusters, right?
Exactly, that's a good point. Yeah.
Okay.
It increases the number of clusters. I perform these moves using integer programming and I improve the solution by 3,000 edges. I mean, in the previous slide, we improved by 2,000 edges in 1 minute. It took me 5 days to improve by 3,000 edges. So improvements are harder to come by. But as you notice, this increases the number of clusters. So this is not a solution to the contest. So I needed to do a final step to reduce the number of clusters. Okay. And for that, I wrote a third integer program that actually models the original challenge exactly. Basically, you can have a variable that tells me whether a vertex is assigned to cluster K or not. A variable tells you if it's assigned to the garbage cluster, some variables that tell me if I need to count this edge because they're on the same cluster, and also need some variables that tell me whether two vertices cannot be counted as an edge because one of them is assigned to cluster K and another one isn't. Okay, this is a bit complicated, but the point is that if you do it this way, you need too many constraints. Basically, you will need like the number of edges times the number of clusters just to be able to, well, to express these constraints and variables. There's too many. The trick here is to use a different encoding. Instead of using one hot encoding for the cluster, I will use a binary encoding. I will look at, okay, these 786 clusters, they can be described with 10 bits, okay? So instead of having a variable that tells me whether U is assigned to cluster K, I'll have variables that tell me whether the ith bit of the cluster assignment of U is set to 1 or not, okay? And after you do this, then you can reduce the number of constraints and variables to something manageable. If you want to know more about the details, I'll describe it later. But if you always think that you model the original problem, you can load it in the solver. It's still too hard to solve. What they did is to fix the partial solution. Basically,
So this is literally binary encoding of the index.
it's binary encoding of the cluster number, cluster layer.
Oh, cluster number, not, okay.
Yeah.
But that's 796. Binary encoding of 796.
Well, I said 10 bits, like because 2 to the 10 is more than 700.
Okay, okay.
Anyway, if you do this, it's still too hard to solve, but you can basically fix part of the solution by using the solution that you obtained before and optimize over the rest. And this is how I found the final solution.
But now there's no linear programming.
It's an integer program.
Yeah, okay.
Yeah, it's much harder to.
Okay.
Actually, for this last step, you could also do some kind of greedy algorithm, and it won't give you something much worse.
Mhm.
But I wanted to find
Mhm.
the best that I could. Okay, so in the end, basically, I found a solution that is probably within 2.8% of optimal in the minimization sense, or 1.6 if you consider maximization version. I suspect that the true answer is much closer to the solution that I found than to the lower bound, but I don't know. If I knew, it would mean that I have a better lower bound, which I don't have. I will just mention that there's a recent technique called per-clustering that has been developed for additional clustering on complete graphs without weights. And my question here is whether basically they show that there are certain set of vertices that need to be clustered together, or they cannot be clustered together in an optimal solution. But the techniques don't extend to incomplete unweighted graphs that we have. They only work in a special case, let's say a correlation clustering, when basically you have an edge or not between every pair of nodes. So my question is whether we can do this in the weighted case, because we could also basically solve a smaller instance, because the per-clustering would allow me to reduce the size of the instance and then apply everything I have done to a smaller instance and solve it optimal. Okay, so that's all I had to say for now. Thanks for listening. Let me know if you have any questions.
Oh, very timely.
There are questions online?
Yeah, so if anyone has a question online, we can take a question or two.
There's been no questions in chat so far. There was, oh, Tatsuo Okubo, you have a question? Go ahead. Oh, that was just a clap.
So I'm curious whether the runners up use very different methods.
Yeah,
or very
I'm
similar?
curious too, actually.
Yeah,
yes.
let's-
Are they here? Is Ben?
Is Tatsuo or Ben here?
Yeah, my solution was very different, so this was really interesting to see. Briefly, it was like sorry, say again.
No, I just wondered if you could say a couple words about your solution.
Yeah, it was based on framing it as a quadratic assignment problem. So it was very similar actually to some of the graph matching stuff that some of you have heard me talk about before. But essentially matching the actual network to a sort of fake graph that sort of this complete click graph that David mentioned. So the graph where everything within a column is connected, and that ends up being the same as trying to maximize the number of connections within those columns. And then I added some similar constraints to satisfy the, each cell type you can only have one of each cell type in those clusters.
Did you also use an internet programming solver, or?
No, this was based on an algorithm called FAQ from Joshua Vogelstein in like 2011, I think. So that was it was a approximate quadratic assignment problem solver.
But your constraints are linear, or do you have a quadratic penalty, or how do you do it?
Trying to think. I feel like, yeah, it might take a while to explain, but basically the constraint is, or the actual constraint is that you are optimizing over the space of like permutation matrices, and the relaxation is the space of doubly stochastic matrices. So I guess it's kind of a sort of like a linear programming relaxation. But it's an approximate algorithm for solving that. And then at the end, you have to project back to permutation matrices. So I guess it's working in a very different space, but maybe there's a way that you could frame it in those terms.
And the fact that these two different approaches landed on almost the same result.
That was going to be my question. So they were actually the solution was quite similar.
Oh, that's a good question. Actually, I can publish all the solutions as well, so we can compare them.
Yeah, that'd be awesome. I'm curious if they're similar or not.
Yeah, and if we're close to optimal, I guess we need to pick one of the solutions or some hybrid of all the solutions and incorporate it in our assignment, and we can declare a victory for mapping the cells to columns.
Ben is here. Maybe we could ask Ben to. Or was he on this solution or a different one?
Ben also did on the same,
Oh, okay.
So what?
yeah, same problem, right?
Yeah.
Ben got
The
the
second.
very close solution, just short few hundred synapses.
What about Tots?
Yeah, oh, yeah, I thought Tots was speaking, so maybe I got confused.
Yes. Hi, Sebastian. Hi, Mana. Hi, everyone. Can you hear me okay?
Yeah.
Yes. So our approach was similar to what David mentioned, which is focus on each neuron at a time and then solve assignment problem. So if you focus on one cell type at a time, you're not violating any constraints. And we were just trying to come up with, and that was, that solver was very fast. So we didn't use any particular solver. We just used SciPy's linear assignment solver, which was very fast. But we try to play around with the order in which you choose the cell types. And if you do it greedy algorithm, it gets quite stuck pretty easily. So we added a lot of randomness. So like epsilon greedy, it's a very high value of epsilon to randomly choose cell type to focus on, solve a linear assignment program, and then go to the next type, solve it again, and then just keep on doing that until it converges to some solution. So it was very similar to what David mentioned, but we didn't have all the bells and whistles that he had.
Wait, if you randomly choose a cell type, you never get stuck?
You keep on doing that, and the so you pick a cell type, you unassign all of them, and then pick solve a linear assignment problem and assign them. Then you go to the next cell type, you unassign all the neurons of that cell type, and then solve the linear assignment problem, assign it, and just keep on marching that.
Sometimes your cost can go up.
Yes.
Is that right?
Yes, and you basically keep on doing that until your increase in the objective function stops increasing.
So you have to allow yourself to be not greedy. You have to allow yourself to get worse.
Exactly. Yes. Yes.
How close was that solution?
It was also within maybe 1/10%.
A few thousand, maybe like 200,000.
Yeah, let's see. Yes, so this was, yeah, it's 0.2%.
So what about Alex?
His solution was also actually fairly close, and I have a few more solutions that I didn't post on the leaderboard. They'll be lower. Okay, so there's a new challenge. Everyone has the opportunity to take the first place in the next one. Don't feel bad if you have not won this challenge. I know David from 15 years ago used to win all these coding Olympiads, so it's a tough competition. But we have a small trophy for you. Thanks for Amy and Marisa for making it. This priceless.
No, I know.
One of.
I hope I don't lose it at the airport. This was
Yeah. All right, so this wraps up our live stream, and we'll move to lab meetings.
Can I,
Thanks, everyone.
can I say
Wow,
one
that's
more
nice.
thing before we wrap up our live stream?
Yeah.
So we did have one question that was submitted in the RSVP form that was actually about the bank data set from Nesterov. And the question was approximately how many neurons are there in the bank? And Wei came through with an answer there that we expect there to be about 150,000 neurons in the bank data set. And then one last thing I wanted to say is if anybody at the live stream is going to be at the Berlin Connectomics conference, you definitely want to catch up with Ari and Minsu Kim and Albert Lin, and there may even be more posters from Mala and Sebastian's lab, but there'll be a couple of posters there. So catch up and geek out on the connectomic stuff. I wish I could be there too, but I won't. So just someone have a beer for me. And with that, we'll wrap it up. Thanks everyone for joining.